Of reaction are how quickly reactants are used up or how quickly the products are made. We can actually work out the mean rate of reaction by looking at the quantity of the reactant used divided by the time taken, or the quantity of the product formed divided by the time taken. Remember, the units of rate of reaction is grams per second or centimeters cubed per second or moles per second, depending on what you're looking at. Factors that affect the rate of reaction include temperature, concentration, pressure for gases only, surface area, and a catalyst. If we increase all of these, we increase the rate of reaction. Remember, if we increase the surface area, we are grinding up a solid to form more of a powder shape. Collision theory. This is the idea that particles must collide to react. The activation energy is the minimum amount of energy needed for a successful collision and therefore reactions to occur. Key idea here is that if there are more successful collisions, you have a faster rate of reaction. A catalyst increases the rate of reaction without being used up. It lowers the activation energy that is needed for successful collisions and therefore provides an alternative route for a reaction to occur at a lower energy. Reversible reactions show us that whatever forms as a product can be broken back down to reform the reactants. We have a symbol that is a forward and backward arrow, and you can see that on screen here. You do need to recognize this. A key example of a reversible reaction is hydrated copper sulfate that forms anhydrous copper sulfate and water, and anhydrous copper sulfate and water can chemically combine together to form hydrated copper sulfate as well. Exothermic reactions release energy in the form of thermal energy to the surroundings, and this makes the reaction feel hot, whereas endothermic reactions actually take in that energy and absorb it from the surroundings, so they start to feel cold. You need to know that in reversible reactions, if the forward reaction is exothermic, well, the backward reaction will be endothermic. Equilibrium is in a closed system, the forward and backward reaction occur at the same rate. And this is often called a dynamic equilibrium because the forward and backward reaction happen simultaneously. A closed system, remember, is just when you have a chemical reaction that is in a container that has a lid, so no external factors can affect the environment. A key idea here is that the amount of reactants and products stay constant because it's in a closed system. Changing concentration, temperature, or pressure can actually shift the equilibrium to favor either side. This is a key idea of Le Chatelier's principle that states that equilibrium moves to oppose the change. So if we increase the temperature, the equilibrium will shift to decrease the temperature. If we increase the pressure, well, the equilibrium shifts to the side that has less number of moles or lower concentration. You can see that from the balanced equation. And this is an idea, especially those of you who are studying higher, that you need to know.
Remember, if the concentration of one of the reactants or even the products is changed, the system no longer is at equilibrium, and the concentration of all the substances will change until that equilibrium is reached again. So if we look at decreasing the product's concentration, more reactants will actually react together until equilibrium is reached. If we increase the reactants, however, more products will be formed until equilibrium is reached again. You guys might be expected to predict which side will be favored in terms of equilibrium if we were to reduce or increase concentration.
If you increase the temperature, a similar thing happens. The equilibrium shifts to the endothermic side, and this is to counteract the change of increasing the temperature. If you decrease the temperature, the equilibrium shifts to the exothermic direction. And you can think of it as if you increase the temperature, you want to almost cool the reaction down. That's kind of a way to remember it.
The equilibrium can also change if we change the pressure on a system. If we increase the pressure, remember this is only for gases, equilibrium will shift to the side with fewer gas molecules. Whereas if we decrease the pressure, well, the equilibrium shifts to the side where there's more gas molecules. There are two parts of this practical, the first being a colour change, and sometimes this is referred to as the disappearing cross method. So you want to measure a set volume of sodium thiosulfate from a measuring cylinder and add it to a conical flask, and then add a set volume of hydrochloric acid. You then, as soon as this is done, you want to measure the time it takes for the solution to become a cloudy yellowish colour. This shows the reaction has reached its point, and you shouldn't be able to see the cross that's underneath the conical flask. You want to record the time and repeat this and calculate a mean, and then repeat the whole process at different concentrations. This is what your independent variable is going to be, the concentration of sodium thiosulfate. The dependent variable is what you're measuring, which is the time taken for the cross to disappear. A control variable in this case would be your temperature, the total volume of your solutions. Also, anything that can affect rate of reaction is what the control must be. Just remember what you're investigating is just one of those factors. Essentially, the higher the concentration, the faster the rate of reaction is because there's more frequent collisions. So the next part of this practical is looking at measuring the volume of gas that's produced from a reaction. So the first thing you want to do is measure a set volume of hydrochloric acid using a measuring cylinder, add it to the conical flask, and then add a set mass of calcium carbonate to the flask and immediately connect the gas syringe and start the timer. You're collecting the gas every 10 seconds and recording that volume in a table and repeating this to calculate a mean. You want to repeat this again at different concentrations of hydrochloric acid. You want to make sure that your control variable is the volume of acid used, the temperature as well, and also the mass and surface area of calcium carbonate, because remember, surface area can affect the rate of reaction just like temperature can. Again, the higher the concentration, the faster the rate of reaction, and therefore more gas will be produced.
Okay, guys, next topic is organic chemistry. If you're enjoying this, by the way, so far, feel free to give the video a thumbs up and share this video with someone else you know who's revising. And of course, subscribe if you haven't already. And thank you so much. Let's talk about crude oil. It's a finite resource, meaning it will eventually run out, and it's made from ancient biomass, specifically plankton that has accumulated for millions of years. But essentially, once we've used it all, it will be gone. So it is finite. It is a hydrocarbon, meaning it's a compound containing only hydrogen and carbon, which are covalently bonded together. An alkane, for example, which we're going to talk about more in a second, an alkane is a saturated hydrocarbon with only single carbon-carbon bonds. And the general formula for an alkane is CnH2n plus 2. And essentially, crude oil is a mixture of these hydrocarbons. We're going to talk more about this later. Combustion is a type of chemical reaction where we burn something, specifically a fuel or a hydrocarbon in this case, and it releases thermal energy from the chemical energy stored in the fuel. Now, there's two types of combustion reactions you need to know. The first being complete combustion, where the hydrocarbon fuel is reacted completely with oxygen in a plentiful supply to create carbon dioxide and water vapor. Incomplete combustion, however, is when there is a lack of oxygen. So the hydrocarbon reacts with some oxygen, but carbon soot is produced as particulates, which can be damaging to our airways if inhaled. Carbon monoxide as well is also produced, a toxic, odorless and colorless gas, and water is also produced here. Fractional distillation is a separation technique used specifically to separate the fractions or sections of crude oil into different chain lengths based on boiling point. So remember, crude oil is a mixture, and in its raw state, it's not very useful, hence the word crude. So the fractions that you need to know include from smallest boiling point to largest, and therefore the smallest chain to the largest chain, is liquefied petroleum gas, petrol, kerosene, diesel, fuel, and bitumen. And you might recognize some of these as well because they are useful fuels that you may have heard of in things like cars and buses, especially petrol, for example. So we have shorter hydrocarbons with lower boiling points. They are more flammable and less viscous, which is why it's so useful to separate crude oil in the first place, so we can get a wide variety of uses from those smaller hydrocarbon chains. However, longer hydrocarbon chains have a higher boiling point, they are less flammable and more viscous. So again, still useful in that sense. However, smaller hydrocarbon chains are way more useful, and we actually go through another process called cracking to make those longer hydrocarbon chains into smaller, more useful ones, and we're going to talk about this now. So cracking, like I said, is breaking down those long chains of hydrocarbons into smaller molecules, and this is important to make more fuels that we need. And as a result of cracking, we have a long chain hydrocarbon, and it produces two sections. We have the alkane that's shorter in length, but we also form an alkene as well. And this also is useful for making feedstock for polymers. Triple only topic, feel free to skip ahead if this is not needed for you in your exam. So alkenes, these are a type of hydrocarbon, however, they are unsaturated, meaning that they contain a carbon-carbon double bond, and this is a covalent bond, very strong. So the general formula here is CnH2n, and N is just like any number. Remember, the main difference between alkanes and alkenes have the double bond, but they have less hydrogens around them, hence the phrasing unsaturated. An example of alkenes are ethene, propene, butene. You only really need to know up to those the heights of 4 carbons in that sense. When you name alkanes, just remember it's the same prefix, so eth, prop, bute, but you also have meth as well in terms of methane. There's no methane, remember, because there is only, you need 2 carbons, right? So you can't have a carbon double bond if you've only got 1 carbon. If you'd like to learn more about this, I've did a whole video on it if you need more time, but that's kind of the overview. We can test for alkenes using bromine water. Bromine water, remember, is a brownish, orangish, clear liquid that decolorizes if there is an alkene present. Remember, it's already clear, so never say the word clear. Say decolorizes or becomes colorless. Remember that also alkenes form different compounds that are no longer hydrocarbons because they have additional elements to them. So in the case of ethene reacting with bromine, you would form dibromoethane. And this is because the double bond has broken open to form a new bond that can now incorporate that element. Alcohols are compounds that have a functional group OH covalently bonded to a carbon. Remember, a key example of an alcohol is ethanol. You've probably used before throughout your GCSEs, and it has the suffix ol, so ethanol. It tells you that it's an alcohol because of this ending of the word. Uses of alcohols include solvents, fuels, and also alcoholic drinks. Carboxylic acids, another type of compound you need to be able to recognize. So they also have a functional group, which is COOH. And a key example is ethanoic acid. These are weak acids. Ethanoic acid is actually vinegar, you guys, a science word for that. And because it's a weak acid, it has a pH of less than 7, but it's a weak acid, so it only partially ionizes. Addition polymerization is a reaction where many alkene molecules join together to form a really, really long chain structure, or a polymer essentially. So the double bond in the alkene will break open and it will form this long chain polymer. So, for example, ethene becomes polyethene. And the N number that you see, that little N, it just signifies how many chains there are, like how many sections. And because it's a polymer, each of those, the ethene itself, is the monomer. It's just making up a big, big chain of these. Condensation polymerization, another triple topic, guys, is when the monomer joins to produce a small molecule. So you have the small molecule being water. Key examples are proteins that are made by this reaction, condensation, and also polyesters.
So amino acids are building blocks of proteins. Proteins are a polymer. Those amino acids are monomers. The functional group of an amino acid is an amine group, which is NH2, and also a carboxylic acid group, COOH. A key idea here is that amino acids are the monomers, and they join together through covalent bonds called peptide bonds that are strong to make the protein chain. DNA is also a polymer, which is naturally occurring alongside proteins, but also starches as well. Remember, starch is found in plants and is made of glucose. Polymers, in the case of DNA, are made from nucleotides, or a monomer, which consist of bases, A, C, T, and G, phosphate, and sugar deoxyribose. The idea here is that there are lots of naturally occurring polymers, and you need to know that natural ones are things like plastics. Polymers are essentially just large molecules of repeating units as well. Next topic, hope you're enjoying this so far. So a pure substance is one element or only one type of compound or atom. So a key idea here is that if it's a pure substance, they will have a distinct sharp melting point or boiling point on a heating and cooling curve, not a great gradual or varied boiling point or melting point. And this is because there's only one type of substance that's either boiling or melting. This is not the same as a mixture. Mixtures have actually a range. They almost have like a gradient of a boiling point or melting point because there's so many different parts to that mixture. Formulations are chemicals that are a mixture designed with a specific purpose. Think of things like medicines, paints, fuels, cleaning products. They have exact proportions which are important for the role that they have. Chromatography, which we're going to talk about later in a required practical, is actually a method used to separate mixtures of soluble substances. A key idea here is that different substances essentially travel at different speeds based on their solubility, and they can be used to identify unknown substances. So an RF value can also be be calculated by doing the distance travelled by the substance divided by the total distance travelled by the solvent or the solvent front. More on this later. Gas can be tested for using a lit splint, and you will hear a squeaky pop sound. Oxygen gas can be tested for using a glowing splint, and it will relight. Dioxide can be tested for when we bubble it through lime water. It will turn lime water cloudy. Gas can also be tested for using damp blue litmus paper. It will start to turn red and then eventually bleach white. Tests are used specifically to identify some metal ions or cations. So lithium, sodium, potassium, calcium, and copper compounds, they all have very clear, distinct colors, and flame tests help us identify them. So copper compounds result in a green flame. Calcium has an orangey red flame. Lithium has a crimson reddish flame. Sodium has a yellow flame, and potassium has a lilac flame. The problem is here, if you actually have mixed samples, it can actually mask the colors of those flames. If we have sodium hydroxide, we can actually use this solution to identify some metal ions or cations. The solutions of aluminium, calcium, and magnesium ions form white precipitates when sodium hydroxide solution is added to them, but only the aluminium hydroxide precipitate dissolves in excess sodium hydroxide solution. You need to know the different formed colored precipitates. So in the case of solutions of copper 2, iron 2, and iron 3, when sodium hydroxide solution is added. So copper 2 will form a blue precipitate, and iron 3 will form a brown precipitate, and iron 2 will form a green precipitate. Another test is using carbonates to react with dilute acid, and this will form carbon dioxide gas. Again, you can test for carbon dioxide gas using lime water. Ions in solution produce precipitates with silver nitrate solution when they are in the presence of dilute nitric acid. Silver chloride has a white color, silver bromide is cream, and silver iodide is yellow. Sulfate ions in solution produce a white precipitate with barium chloride solution when they are in the presence of hydrochloric acid. So far, we've talked about different methods of chemical analysis, but there's actually more detailed, more developed methods that are called instrumental methods, and these help scientists identify in a faster and more accurate way. So flame emission spectroscopy, this again is just for triple students. It's an example of an instrumental method, and it's used to analyze metal ions in solution. The sample itself is put through a flame, and the light that's given out through the machine is passed through the spectroscope. And the output has essentially a reading which we can then use to measure the concentrations of each of the metal ions in the solution. You should be able to interpret an instrumental result given appropriate data. First thing you want to do is draw a pencil line at the base of the chromatography paper, about a centimetre or so from the bottom and from the edges so the ink doesn't run off. You then want to draw little crosses along the line so they're evenly separated, and place a dot of each ink spot or dye spot onto the line itself where you've annotated it in pencil. You want to label those dots as well so you know what they originally were. You want to then place the paper into a solvent, sometimes water, sometimes acetone. Different solvents are able to do different things and dissolve different solutes. So you want to make sure that the solvent line is below the pencil line so the ink doesn't flush off the end. You then want to measure the distance traveled from the bottom of the page all the way to the top, and you leave this for about 15 minutes or so, and you should actually see the solvent front. This is the line where the solvent gets to, just before it gets to the very, very top. So you want to draw a straight line, and essentially what you're doing is you're measuring the RF value, so the distance from the line we drew in pencil at the beginning to the solvent front, and then also the distance from that line to each point, each of those different colors, and you divide them by one another. I mentioned this in a previous slide, and you can work out your RF value from there. Chemical tests, I've mentioned this already, but just as a recap, here you are. Atmosphere is made up of mainly nitrogen, which is 78% in abundance. 21% was oxygen, and 1% roughly is other gases like argon, carbon dioxide, and water vapor. The key idea here is that oxygen supports the combustion of fuels and also respiration. But remember that oxygen in the early atmosphere wasn't actually very prevalent. We're going to talk about this now. So in the early atmosphere, it was mainly CO2 and water vapor, and this is because of volcanic activity, and a very small amount, if no amount, of oxygen, because there was a lack of plants, and low amounts of plants means less photosynthesis. So it's only through time that this has increased, and we're going to talk about this now. CO2 plus 6H2O goes to make C6H12O6 plus 6O2. Remember, photosynthesis happens in green plants and algae, and over millions of years, oxygen has built up through this way. Processes in how carbon dioxide decreases. It dissolves in oceans. This is a carbon store. It also forms carbonate rocks, so sedimentation or sedimentary rocks. And also photosynthesis absorbs a lot of CO2 and converts this into oxygen. Gases include carbon dioxide, methane, CH4, and water vapor, and they are useful in trapping the Earth's heat from the sun itself, the solar radiation. Some of that heat is retained to make sure that we have the ambient temperatures on Earth. However, if we have too many greenhouse gases, that's when the temperature on Earth increases, and this is due to human activities. So just in short, but we'll go into this in more detail, landfills, cattle farming, fossil fuels all increase the amount of heat because they all release greenhouse gases that trap the sun's radiation. fossil fuels, which release carbon dioxide and water vapor, deforestation that reduces the number of trees and therefore less photosynthesis and therefore less carbon dioxide is absorbed. Agricultural reasons such as cattle farming increase methane production, and rice paddy fields also increase methane production, and also landfills release methane as well. And also landfills can be used because we have less trees, so we need more space for landfills, and that can also lead into the deforestation angle too. That is the rising global temperatures, the sea levels rising because of the melting ice caps, extreme weathers including drought, floods, wildfires, earthquakes, and landslides. Causes for this is the increasing greenhouse gas as well as the greenhouse effect. CO2 emissions caused by a person or activity is what we refer to as the carbon footprint. A way to reduce this is to include renewable energy resources, public transport, reforestation and planting new trees, and energy efficiency. So the main pollutants you need to know about include carbon monoxide, CO, sulfur dioxide, SO2, nitrogen oxides, NOx, or you can have nitrogen dioxide, NO2, or nitrogen oxide, NO, and also just particulates such as carbon monoxide is a poisonous, odorless, and colorless gas. And it actually prevents oxygen being transported around in the red blood cells. Sulfur dioxide causes acid rain. It damages buildings and lakes and kills aquatic animals such as fish because sulfur dioxide mixes with water vapor and causes that acid rain to occur. Nitrogen oxides also can cause acid rain and smog, which is like smoky fog, and can lead to global dimming alongside particulates. So this not only produces respiratory issues, but again leads to global dimming as well. It contains fuels or crude oil that we extract. We also get minerals or metals from the earth and water. Sustainable development is this idea that using resources without them running out. So replanting trees, catching only mature fish first, or having fishing quotas, and minimizing overall environmental damage. Potable water is water that's safe to drink. It's not pure water in a chemical sense because it contains other dissolved substances, such as salts and microbes, but it is safe to drink. In the UK especially, we get a lot of our water sources from the ground itself, so the lakes and rivers, and it's actually producing potable water by sterilization, such as UV or chlorination, and also filtration as well. So we also can use other methods of making potable water, including desalination, which removes any excess salt, or by a process called reverse osmosis that uses membranes to essentially remove any unwanted particles. Sewage has to be treated carefully because it contains contaminants. It also contains bacteria and it's unhygienic. It can cause illness. So it has to be treated before it's disposed. So the first few steps that you need to know is that screening and grit removal is the first step in sewage treatment. This removes any large debris. Sedimentation is then the next step to produce sewage sludge and an effluent. The effluent is the liquid and the sewage sludge is the kind of particulates that are left at the bottom of the tank. The next stage is anaerobic digestion of the sewage sludge by bacteria, and then aerobic digestion, which is a biological treatment of the effluent that's left behind. A finite resource. High-grade ores are often extracted and used first. Lower-grade ores are still useful, especially if we need copper. So the first method is looking at phytomining. Phytomining uses plants to absorb the metal compounds. The plants are then harvested, collected, and burnt, and they produce an ash that contain that metal compound. The next one is bioleaching, and this uses bacteria to produce a leachate solution that contains the metal compound. This leachate can then be processed to gain that metal. And this is by a method called electrolysis. So you could, for example, get copper from the solutions of copper compounds and displace that copper with scrap iron. Or assessments, or LCAs, are carried out by companies and corporations to assess the overall environmental impact on a product at each stage of its life. So the first part is extracting and processing the raw materials. Then there is the manufacturing and packaging of the product itself. Then it's the use of the product and the operation of it during its lifetime and how it works. Then it's the disposal at the end of the product's life, and not just where you dispose it, but how you do that. So the transportation to either recycle it or put it in a landfill. So different resources are needed throughout the entire life cycle of a product, and you could be expected to compare different life cycle assessments. The first way is recycling, also reusing materials in the first place, using less packaging from a product design perspective, and also using renewable resources. So remember, metals, glass, clay, ceramics, plastics, all of these come from raw materials on Earth, and it requires a lot of energy to process them to create the product that we want. So we also have to think about the environmental impact of this in terms of mining and also just disposal. And it kind of links to what I talked about in terms of life cycle assessments. Remember that recycling is often seen as the best approach. However, Recycling still requires transportation to a recycling plant and then processing it by crushing it down, reforming it, which all requires energy that is essentially coming from fossil fuels being burnt. So the best way to actually minimize our overall impact is looking at using less things that we don't need. Is the destruction of materials by a chemical reaction due to the environment. So rusting is a really good example of this. It's both with air and water, and it causes iron to rust. You might have seen rust before. It's got kind of like an orangey color. It can actually be prevented by coating different layers on the product that you're trying to prevent rusting. So greasing, paint, electroplating, any lubrication that will actually prevent it from rusting itself, forming a physical barrier. Aluminium has an oxide coating, and this protects the metal from further corrosion. That's a good example that you should know. Some coatings also are reactive and contain more reactive metals to produce a sacrificial protection. This is a good example, say, for example, zinc. It's used to galvanize iron. Alloys are the most common form of metals in everyday objects. They contain multiple metals. So steel is a good example of an alloy. It contains iron and other metals. Brass is also another example. It contains copper and zinc. Bronze, again, copper and tin. Even gold jewelry is often an alloy of silver and copper and zinc. You can often hear about jewelry being in like carats, like 24 karat gold being 100% pure, whereas like 18 karat is about 75% gold. So the reason alloys are used is because they have a mixture of properties. You should be able to understand that why these alloys are used is because they have different size atoms that distort the layers. They're harder for those layers to slide across one another, so they're often stronger as opposed to other pure metals that are just soft. So that's kind of why we use alloys. You might be expected to suggest a reason or a use for each of these alloys. These are clay based. They are included in like pottery, bricks as well. First, you want to shape the wet clay, and then you will just heat it and it will set in a furnace in that shape that you want. Let's talk about some other objects such as glass. So glass is actually made of something called soda lime, and this is by heating sand and sodium carbonate and limestone, and this is just a mixture that's heated together. Borosilicate glass is actually made from sand and boron trioxide, and it actually melts at a higher temperature than soda lime glass, so there's just a different method of creating glass itself. Let's talk about polymers. So these are more flexible, a bit more lightweight. And the properties of polymers really depend on the monomer it's made from. Specifically, you've got low density polymers, for example. You can use something called thermosoftening polymers, which help the object to melt when they're heated, or even thermosetting polymers that don't melt when they're heated. So again, depending on the properties it's made from. We also want to talk about composites. So these are a combination of materials. So composites specifically or when you have those two different materials, it's called a matrix or a binder, and it's surrounding and binding together the different fibers reacting with hydrogen going to make ammonia and vice versa in the backward reaction. Conditions needed are 450 degrees Celsius, 200 atmosphere as pressure, and an iron catalyst. It's worth mentioning as well that on cooling, the ammonia liquefies in the reaction tank and it's removed so it can be processed and used as a fertilizer. The rest of the hydrogen and nitrogen are actually recycled within the tank so it can be used again for the reaction. NPK fertilizers are useful in agriculture. They contain nitrogen, phosphorus, and potassium. Nitrogen is used for leaf growth, phosphorus is used for root growth, and potassium is used for fruit or flowering growth. Production of NPK fertilizers is difficult because sometimes you have to react it with acids, with ammonia or phosphates. So potassium salts are mined and used directly. However, insoluble phosphate rock must actually be treated with nitric acid or sulfuric acid or even phosphoric acid to produce that soluble salt that the plant can then absorb. Use a pH probe or universal indicator to identify the pH of different samples and record this in a table. You then can also look at any dissolved salts or minerals by collecting a sample of the water, measuring the mass at the beginning and the mass at the end to identify the amount of dissolved salts. This can then be recorded in a table. About the sample of water, once it has been analysed for pH and also salt content, we then can purify it. So any thick or heavy debris can be removed, and the sample itself will be placed into a conical flask and attached to a delivery tube and a test tube. You want to place the test tube into a beaker that's filled with ice and water, and this is going to act as a condenser, or you could simply use a condenser. You want to heat the water sample gently using a Bunsen burner until it begins to boil. The water vapor will then travel through the delivery tube and condense into pure water in the cold test tube and reform as liquid water as opposed to the vapor. You can then retest the pH and mass of dissolved solids in the distilled water to confirm its purity. And that's it from me today. I've been the GCSE science teacher and you have been curious. I hope you enjoyed this video. If you did, feel free to like it, share it with someone else, and also feel free to subscribe. Good luck for your exams, and I'll catch you in the next one.